So, so our next speaker is Peter Miller, and this is continuation kind of the previous talk. How are the roguewaves and solitons and solutions interpolating between them? Part 2, distinctive features. Okay.
Thank you, Gana. So I want to thank the organizers of the workshop. You know, it's a little bit of a shame that this program had to be delayed, but it's very nice to see everybody and have this opportunity to have some interesting discussions in the meantime. Okay. So this is a report on joint work with Deniz Bilman, and as he mentioned, I'm going to kind of continue with what he was discussing. So this is part 2 of the talk. It has to do with looking at the differences of these solutions that depend on the continuous parameter m. When you change this m value, how do the solutions look different? He was concentrating really on how they were the same. I'm going to talk about how they are different. So just to review, or in case you had to miss the talk before, we were talking about a particular family of solutions of the focusing NLS equation that are encoded in a Riemann-Hilbert problem. And so that Riemann-Hilbert problem has a jump across a circle of radius bigger than 1, which we take to have clockwise orientation. And the parameters of the Riemann-Hilbert problem are a 2x2 constant matrix G that has unit determinant and satisfies some symmetry condition like this. The star means you take the conjugate of the entries of the matrix, okay? No transpose. Anyway, and there's a fixed a real parameter m greater than or equal to 0. There are also, of course, the space-time parameters for the equation in the Riemann-Hilbert problem. So that problem is to look for a matrix which we'll call P of lambda that has the properties that it's analytic for lambda outside of this circle and inside of the circle. So in this formulation of the Riemann-Hilbert problem, maybe to compare with what came in the last talk, we have removed this cut already, okay? So there's only the circle here. And the matrix P takes continuous boundary values on the circle from inside and also from outside. So because of the clockwise orientation, the inside is going to be the minus boundary value here, and outside will be the plus boundary value. And those boundary values are supposed to be related by the following jump condition. So P plus is equal to P minus times this jump matrix, and the jump matrix has the structure that we heard about in the last talk. So there's the exponential nonlinear Schrodinger exponential conjugation factors here. There's also conjugation by this Blaschke product, lambda minus I over lambda plus I to the power m sigma 3. So if m is an integer, that's something that makes complete sense, and otherwise it requires some interpretation. And here we're taking the cut to be exactly this segment, that's vertical segment connecting I and minus I. Well, that's completely contained within the circle, right? So we're talking about the values of that cut function on the circle when we discuss the boundary, the jump condition. So that makes sense as well. And then we're conjugating this all with this constant matrix G here. Okay, and then the matrix P is normalized to the identity as lambda goes to infinity. So then from the residue at infinity, we take the 1, 2 entry, which goes to 0. We multiply by lambda to give it a fighting chance and take the limit, lambda to infinity, multiply by 2i, and that's a function q that satisfies, because of these factors here, it satisfies the focusing nonlinear Schrodinger equation, okay? So that's really the dressing construction. That's really why these factors lead us to this equation. Okay, so that's the problem that we were discussing. And then there are some special cases that we know about. So when m is a half of an integer, so k over 2, where k is a non-negative integer, then this q is a kth order pole soliton solution. Okay, so like a higher order soliton solution with conjugate eigenvalues plus or minus I. Now that's not terribly important that we're choosing the plus or minus I here. You can use a Galilean transformation to move them to any other complex conjugate pair of points in the complex plane. So that's quite straightforward. So we'll just normalize them in this way. And then if m is equal to 0, that's the trivial solution. Q is exactly equal to 0. So this is a plot for, as I think this is for, this is a k equals 8th order soliton. Okay, so that's what that is. All right, and then on the other hand, if you take this m parameter to be a half integer plus a quarter, so you shift everything by 1/4, then this Q is instead a kth order rogue wave solution. And in the basic case that m is exactly equal to 1/4, then it just trivializes to the constant background, well, okay, exponential background solution. Q is equal to e to the it, okay? So this is a picture here. This is a picture here of the k is equal to 8 order rogue wave solution, okay? Of the same equation, but different boundary conditions, of course, okay? So those are some special cases that we heard about already in the last talk. Okay, now this brings me to a true story, I have to tell you. It's kind of fun. So I was giving some talk about rogue waves in Taiwan, in Kaohsiung, in Taiwan. And before the talk, I was walking. So the university there is right on the water. It's right on the beach. You know, really nice. And I was walking along the revêtement, I guess, there, as it says in the sign, and I noticed this sign I thought was really great. It says, you see, public notice, this harbor is a dangerous deep water region with frequent rogue waves. For your own safety activities, blah, blah, blah. Please observe these safety regulations at all times, okay? So I thought, that's great. I took the picture and put it in my talk. And then after the talk, my host approached me and said, you know, in Chinese, we don't call them rogue waves. We call them mad dog waves. So this is it right here, mad dog waves. And I said, I was thinking, you know, gosh, is it mad like angry or mad like crazy? What exactly is it? But anyway, you know, so that's the idea. So in Chinese, they are mad dog waves. Somehow you can imagine that there's an angry or perhaps a crazy dog that's just jumping out of the water at you. That's the idea. So maybe we can just use that terminology. I like it going forward. Okay, back to the math, right? So yeah, so common features. So this was the topic of the preceding talk. So the solutions Q with this parameter m being just a positive real number, they have interesting common features in the limit m goes to infinity. And it doesn't matter how this m goes to infinity, what sequence we pick, okay? So whether the solution is a sequence of solitons or rogue waves or something in between, it makes no difference. So these are the limits that were discussed in the last talk. So first is the near field limit. So that refers to letting m go to infinity. The order m is going to infinity, but at the same time, you see we're localizing in the xt coordinates toward the origin, right? So we're kind of zooming in on 0, 0, and at the same time, we're letting the order blow up, and then we have to renormalize by this factor 1 over m. But it turns out if you do that and you take this limit m to infinity, then the limit exists, and that's a function capital psi of capital X and capital T, also depending on this matrix G as a parameter. And it's a solution of the NLS equation in the form without the -1 to somehow renormalize the boundary condition, okay? But it's an isomonodromic solution in some way. It satisfies not just the PDE that you see here, but also it satisfies ordinary differential equations that are Panleve-3 related with respect to X and T separately, okay? So this is referred to in this work with Deniz and Liming Ling, for the rogue wave case. So here we looked at the limit when we're in the rogue wave sequence, but then as Deniz also pointed out in his paper with Robbie Buckingham, they looked at the soliton case, found the same result, but with a more general matrix G here. And then the generalization to arbitrary M, not necessarily being corresponding to rogue waves or solitons, is given in our recent preprint. So here's what we called at that point the rogue wave of infinite order. This is its graph at time t, capital T equals 0. That's what it looks like. So it's a transcendental solution. Amplitude is 4, and it has infinitely many of these oscillations like that. Okay. So then the next part where there's universality somehow is this hamburger region. Actually, maybe it's more of an ice cream sandwich because of this kind of concave profile here on the left and right hand sides. But anyway, it's this region in the yellow curve. So this is some region of the xt plane. It's expanding in size as m goes to infinity. So no longer are we localizing near the origin. We're in fact allowing for the coordinates to become large, proportional to m, but in some region which is expanding with m. And that specific region in rescaled coordinates is this yellow hamburger here. Okay, so in that region, as we heard from the previous talk, there's universality in the sense that it doesn't matter whether I'm looking at this picture or something that we might put in between. We'll put a question mark there, so we have to remember to answer that. later on. But anyway, it doesn't matter what I look at. I'm going to see the inside of this hamburger the same asymptotic behavior. Okay. All right. So now I would like to move on to the distinctive features. So the exterior of that expanding hamburger region is a domain that in our paper we call E, okay, curly E like this. So in the rescaled variables where I take X and I divide by M, T divide by M, I call those chi and tau. So in those rescaled variables in the chi tau plane, it's a fixed region, okay? There's a fixed hamburger in that region, and the exterior of that hamburger is the domain E. It's a fixed region of the chi tau plane, unbounded fixed region. So anyway, multiple pole soliton solutions and rogue wave solutions of different orders, they behave extremely differently on this exterior domain. So very different behavior, okay? And I should also include in that these other solutions that are in between somehow, the rogue waves and the solitons, they behave differently yet again, as you will see in the talk. So, okay, so the multiple pole soliton case for in this exterior domain, that was analyzed in the paper of Bilman and Buckingham in 2019. And also there's a preprint you can look at on archive with Wang as well. So I'm going to review those results for you. So what's going on for the multiple pole solitons in the exterior domain? So the first thing I have to do is describe a certain curve in that exterior domain. It's called L sol, okay? And it's related to that exponent that was that Deniz mentioned in the last talk. So this is the fundamental exponent in the Riemann-Hilbert problem. When m is large, we have chi lambda plus tau lambda squared plus I log of b of lambda. This b was that Blaschke factor. So this is a function which has its branch cut between I and minus I on that segment, and it goes to 0. The logarithm goes to 0 at infinity. So anyway, so when chi and tau are in the exterior domain, this function of lambda, this phase function of lambda, it's got a complex conjugate pair of critical points in the complex plane. So if we pick gamma, this capital gamma, to be some Schwartz symmetric contour that joins the critical points, and well, Schwartz symmetric up to orientation. Okay, so I'm going to orient it in the upward direction from the lower branch point to the upper one. Okay, so I'm going to integrate I theta prime along this gamma curve and take the real part, set that to 0. So that's a condition, that's a real condition on these two variables chi and tau. So it's going to define a curve in the chi tau plane, and that curve we call L sol. So it emanates from a particular point, which is this chi sharp tau sharp, this specific point. That's the red dot that you saw. Those four, actually, it's the red dot in the first quadrant for this burger here. So right over here. So there's that point, and it has symmetric images in the other quadrants. Okay. All right. So yeah. So in that paper, what happens is that the exterior domain for the solitons gets split into two parts. Okay. So so the interior part, just to review for you, there was the burger bun, which we called shelves for some reason in our paper, and then there's the meat of the burger, which is called the channels over here. But the exterior for the solitons is divided into an oscillatory region O and an exponential decay region E along this curve L sol. Okay, so you see there's the point chi sharp tau sharp. Here's the curve L sol coming out, emanating into the exterior. Okay, and asymptotically, like really far away over here, this curve L sol looks like a logarithm. Okay, so chi is like ln of tau plus something bounded as tau goes to infinity. So up in this direction, that's what it looks like. Okay. So now what are the results for the solitons? So the first one is on the exponential decay region. So this is really, let me just show you again the picture. So we're talking about this part of the picture now. And of course, out here, this is the x-axis for the problem. So the solution has to decay to 0 exponentially. It's a soliton, right? So somehow what we're saying in this region E, this region Roman E inside of the exterior, is that there's some capital some d greater than 0, sorry, such that q is bounded by e to the minus d times m. So exponentially small solution in that region E, and that's true when m is a half integer. So that's the soliton sequence. And here the constant d can be assumed to be fixed on any compact subset of this exponential decay subregion of the exterior. Okay. And then on the oscillatory region, that's the rest of it. That's the rest of the exterior. So then there's the following result, which can be found in this preprint with Wang and Buckingham and Bilman. So if chi tau is in the oscillatory region, part of the exterior, then when m is a half integer, this q, this kth order soliton, where k is exactly this half integer here, it's approximated to order 1 over m by a modulated elliptic function. And the wave number and frequency are proportional to m, so it's a rapidly oscillatory but slowly modulated elliptic function, and the elliptic modulus tends to 1 as chi and tau approach this common boundary curve L sol, okay? So of course, elliptic modulus going to 1 means that the wave train is turning into a train of solitons, and that's what's happening right at the edge there. So here's just some plots from that preprint comparing the modulus of q with its elliptic function approximation, which I guess, so the red curves, which you can kind of see here. So here's the corner of a red curve. That's the modulus of q, and then the black curve is the elliptic function approximation, if I'm not mistaken. Okay, so comparing this with for m is equal to 2, 4, and 8, which we have to multiply by 2 to get the soliton order. So that's 4, 8, and 16 for some specific choice of the matrix G here. So you see that things are quite close, of course, in this region, and this region between this point and this point at the given value of t for which these pictures are made corresponds exactly to that oscillatory region. Okay, it's an interval of x, of chi, I'm sorry. Okay, so anyway, so that's what happens in the exterior region when q is a multiple pole soliton solution. So that means the m is a half an integer. So now I would like to change gears and talk about what happens if m is a quarter away from a half integer. So that's the other sort of quantized situation. It's the fundamental rogue wave solution case. Okay. So for me to describe this, so Deniz already mentioned that some kind of a g function is involved. And that means that, well, you got to find roots of some polynomials. Unfortunately, it's always what you have to do. So I'm going to now describe that. I'm sorry about the math, but here's what it looks like. So if you're in the exterior region, chi and tau are in the exterior, there's a unique root u, which depends on chi and tau, of odd multiplicity of this 7th order polynomial. So P of u is a 7th order polynomial depending parametrically on chi and tau in an explicit way. So here's the polynomial. I don't want to say it for you. You can read it on the screen. There it is. Okay. So I'm telling you that you can prove that there's a unique real root that has odd multiplicity of this equation whenever chi and tau are in this exterior domain. So we do that in our paper. So then from the u, we define a function v, also depending on chi and tau parametrically in this way, okay? And then we define in terms of u and v, we define a capital A explicitly here and a capital B by taking a square root, a positive square root in this equation down here, okay? So then lambda naught is A plus IB. So it's a complex number in the upper half plane, okay? Also depending on chi and tau. So that's basically the branch point for our g function, okay? So we're gonna let r for square root of lambda chi and tau be a certain square root of lambda minus lambda naught times lambda minus lambda naught. That should be star, I'm sorry, let me fix that for you. Complex conjugate, okay? And then from lambda naught star and this square root function r, which is cut between those 2 points, we define a real phase gamma by this formula here. So chi times a of chi tau, tau times this expression here, explicit so far, up to this septic polynomial whose root we must find. And then there's an integral. So 2 times the real part of I times the integral from lambda naught to I, which is the fundamental soliton value or eigenvalue for the problem coming from the background. And then we have d lambda over r, okay? So for rogue waves, it turns out, since we're sort of wanting to get something that kind of goes to a constant background, it's better to peel off this exponential factor. So we think of psi k as the q times e to the minus it, and we're quantizing the m parameter appropriately for rogue waves here, okay? And it's also good, Deniz mentioned this in his talk as well, to select for this G a specific matrix. So we're going to take q to the power minus s. S is just the parity. It's a plus or minus sign. It's the parity of the order k. And then there's the matrix Q, this rotation matrix Q, okay? So doing that sort of fills in all the symmetry that we want for the fundamental rogue wave, but it's not terribly essential. We could modify and put in some other matrix G here and get similar results. But anyway, the point is that with this factor taken out, this psi k is going to tend to the constant background psi naught equals 1. The 1 is coming also from the choice of this sign S being an alternation between the odd and the even orders. If we fix the matrix, say, Q here for G, then we would get 1, -1, 1, -1 as we alternated the order. But it doesn't matter, just a convenience. So we're going to look at this psi k. Okay, that's the fundamental rogue wave of order k. So our result on that is the following. So the fundamental rogue wave psi k of order k satisfies that psi k of m chi m tau. Yeah, is there a question? Okay. Is equal to, so b of chi tau, you will recall that is the imaginary part of this branch point lambda naught of chi tau. So it's something we get from solving this septic equation. It's a positive quantity. It's like an amplitude times exponential minus I m tau, and then exponential minus 2I m gamma is that phase that we defined, plus order 1 over k, as m goes to infinity in this sequence here, which corresponds to rogue waves. And the error term, this error term here, is uniform on compact subsets of this exterior domain in the chi tau variables. So anyway, when tau is equal to 0, lots of stuff happens, like this term disappears over here. It turns out this is also gone, and this b we can compute explicitly. So the asymptotic formula is a bit simpler. Psi k of m, this should be 0 here, of 0 m tau, okay, is a square root of, m chi 0, square root of 1 minus 4 over chi squared plus order 1 over k. So very explicit thing, and you see clearly that as chi goes off to infinity, this goes away, and we're left with the background value of 1. Okay, more generally, one can show that that this b of chi tau goes to 1, the amplitude goes to 1, and the phase up here, which is really gamma plus 1/2 tau, goes to 0, okay, as chi tau goes to infinity. So the leading term is reproducing this kind of known decay to the background value of psi of 0 of xt is the constant 1 for the exact solution of psi k, all right? So the asymptotic is somehow our sort of chi tau fixed large m asymptotic is agreeing for large chi and tau with the known asymptotic at infinity for the rogue waves, okay? All right, so this approximating formula that I just told you about, this amplitude and phase here, this is a modulated plane wave, and it's got a slowly varying amplitude. This b is a slowly varying amplitude. After rescaling by m, it's got a wave number, which is -2 times the chi derivative of gamma. And the frequency is, okay, 1 plus 2 times the tau derivative of this phase gamma. And so one can check directly from a computation that the following corollary is true. So if you take chi and tau in that exterior domain, and you define a fluid density rho by b squared and a fluid velocity u by -2 gamma sub chi, right? Then these two quantities satisfy the sort of hydrodynamic dispersionless NLS system. Okay, so here's the hydrodynamic dispersionless focusing NLS equations. And so I had to say that because this is a workshop on dispersive hydrodynamics, okay? I guess this is dispersionless. Okay, well, it's good enough, right? But the proof anyway relies on just an identity, which is that the chi derivative of this phase gamma, you can prove that that's equal to this real part of the branch point A of chi tau, okay? So it's a modulated plane wave that satisfies the dispersionless NLS equation in the exterior. Okay, so this result that I just told you about, it extends to this exterior domain E, a result that's valid for the whole family of solutions for, continuous M really, on this hamburger bun region, which we also call the shelves S. Okay, so that's this part, that's this kind of interesting part over here. So that's what Deniz talked about. Remember, he mentioned that there's a leading term over here, and then there's a perturbation term, and the perturbation term is responsible for all these kind of interesting, marks that you see, this kind of pattern of waves. But the leading term is something that matches very nicely onto what's happening out here and also over here, okay? It's really the same dispersionless NLS solution at the leading order in this whole exterior domain. And here's just a picture to sort of illustrate that, right? So here's the computation of that leading term, or the amplitude of that leading term. And here, of course, is the picture of the rogue wave of order 32. So you see this kind of pattern that's kind of confusing you a little bit, but if you squint your eyes and blur this out, it's really just this, okay? It's the same leading term. The only difference that happens across this curve is that there's a certain phase factor of order 1. We call it e to the minus 2i mu that appears on the inside. It's not present on the outside, but it's present on the inside. But also this mu function goes to 0 when you approach this blue curve from inside. Okay. All right. So now just to recall, so a review. So when m is a half integer, then we have a kth order pole soliton solution. It's got 0 boundary conditions, being a soliton as x goes to plus or minus infinity. And its behavior on the exterior domain, E, it splits into 2 cases relative to some curve L sol and its reflections in the axes. So there's a subdomain exponential decay region, and there Q decays exponentially to 0, and that's consistent with the 0 boundary conditions that we know the soliton satisfies. And then on this oscillatory region within the exterior, Q behaves instead like a modulated elliptic function, and that's consistent with the slowly diverging trajectories, as you see in this picture, of all these solitons that are all traveling asymptotically with the same speed, 0 in this case, okay? But they're all packed together, so they look like an elliptic function. All right. Then on the other hand, when m is off by a quarter from a half integer, so then we're in the rogue wave case. And if we renormalize with the exponential factor and put in the right Q to get a fundamental rogue wave, then this is the kth order fundamental rogue wave solution. And it satisfies non-zero boundary conditions. It goes to 1. This psi k goes to 1 as x goes to plus or minus infinity. And it behaves exactly the same way on the whole exterior domain E, which is just like a modulated plane wave. So that's the outside of this picture over here. Okay. So what about the other solutions? I'd like to talk about those in a few minutes here. So in general, we can write this continuous order m in a kind of modular form. We take a quotient q by half an integer and then have a remainder r. So m is a half k plus r. Okay, k is the quotient, r is the remainder, and it's between 0 and a half. So the soliton case is r equals 0. The rogue wave case is r equals a quarter. So if r is neither 0 nor a quarter, then you might think somehow that the boundary conditions at infinity should somehow tune between, you know, the 0 boundary condition for 0 and the 1 boundary condition for a quarter. Maybe modulus of q goes to something between 0 and 1, but that's not true. In fact, we're writing this up now, but anyway, if your r is anything at all that's not 0, okay, then the q is going to tend to 1. Plus something small as x goes to infinity. So this is at time t equals 0. So that's the boundary condition on the initial data. So the error term here, this order 1 over square root of x, this is sharp unless r is a quarter. That's the rogue wave case. And in that case, it's faster decay. It decays like 1 over x squared. And that's great because that means that you're in the rogue wave case, you have an L1 perturbation of the background, but generally you don't. This is too weak of a decay, and it's a sharp estimate here, okay? So we have like non-zero background, but very slow decay. And so except in the soliton case of a half integer for the m, the initial condition satisfies unit amplitude non-zero boundary conditions. And for rogue waves, we have the L1 decay to the background, but in general, it's really slow decay. It's not even an L2, actually, very, very slow decay. So now we may ask this question. So suppose we fix an R value, a remainder that's not 0 and not a quarter, and we let this K index, the quotient, tend to infinity. So how might we expect the asymptotic behavior in the exterior domain E to vary with R in this limit? We've seen 2 kind of special cases, quite different. Well, just as the large X behavior is insensitive to whether you have whether R is any value not equal to 0 or a quarter, so in fact is the large K behavior. So to describe it, this curve L sol is less important than another curve, which we call L trig. Okay, so it's also emanating from this chi sharp, tau sharp coordinate. And it's defined by this equation in terms of the u and the v functions, which you remember came from this septic polynomial. Okay, so this curve, this L trig curve, it's an unbounded curve. It's asymptotic to a line. Chi is equal to √8 times tau for large tau. And what it really is it's just another branch of this curve that separates the shells from the exterior. So the top of the burger bun. So maybe I have a picture, maybe I do. Yeah, so so there's this curve. This is the boundary between the burger bun and the exterior. It's got another branch, okay, which is this L trig function. So that becomes important when we talk about the more general solutions over here, and you see that compared with the L sol. So for r not equal to 0 or a quarter, this exterior domain is divided along those two curves into the plane wave region P, which is below L trig over here. And then there are now two oscillatory regions, O1 and O2. You see them here, okay? So when chi and tau is in the plane wave region, the solution has the same asymptotic behavior as when r is equal to a quarter. That's the rogue wave case. So it looks like a modulated plane wave. In fact, the same modulated plane wave that we saw in the rogue wave case. And when chi and tau is in this O1 region over here, then the solution instead, it has the same asymptotic behavior as when r is 0. That's the soliton case. So here you've got these kind of stripes, this modulated elliptic function going on, okay? So what about this? This is the interesting part. So somehow here it's like a rogue wave, here it's like a soliton, and here what's going on is the question. So on this remaining domain O2, the asymptotic behavior for large K, it's not like either the rogue waves or the solitons. Nobody wins. It's a different thing. It's governed instead by a leading order approximation by a different modulated elliptic function. The elliptic modulus now is going to vary from m equals 0 on L trig, so it's the trigonometric degeneration of the elliptic function, to m equals 1 on L sol, which is the solitonic degeneration, okay? So since L sol bends toward the vertical as tau goes to infinity and L trig approaches this linear asymptote, chi is √8 tau, one thing you can do is you can look at the solution, this asymptotic solution, when chi and tau are large. So we're commuting limits here. I'm sorry, but I'm going to do it, okay? If I commute the limits, then what I find is that the solution, or asymptotic solution, is consistent with this kind of universal long-time asymptotic that Gino Biondini and Dionysius Mentzevinos found in 2017. They were considering solutions of the focusing NLS equation with non-zero boundary conditions, certain kind of solutions, but unfortunately the ones we're talking about today don't fit into that. They just decay way too slowly to the background, so they don't satisfy the hypotheses, but somehow they're consistent with the result, and that points toward a kind of broader universality of those results, okay, those large tau results. So basically, that's my talk. I just have some references for you, and I'll entertain any questions. Thanks.
Thank you very much, Peter. Thank you. So, well, we have a question through the chat from Jan Ribalko. Is it possible to verify the boundary conditions of Q for any finite m, not only say half integers, from the Riemann-Hilbert problem?
Yes, it is possible, and that's precisely how I can say that that if m is not a half integer nor a quarter away from a half integer, we have decay to the non-zero background, but very slow decay, so slow that the difference is not even in L2.
Mm-hmm. Thank you. Any other questions? Okay, so it's.
Can I ask you maybe a general question, Gennady?
Hi, Pavel.
Yeah, so there is a question in the chat. Well, probably it's from
Okay.
Zhenya Ferapontov, I guess, but it's an acronym here, but probably it's Zhenya. Is it possible that the continuous family is an elementary function?
Is it possible that it's an elementary function? I don't know, but I think it's highly unlikely. So, you know, the thing is that in the cases when this m is either half integer or a quarter away from a half integer, it's possible to solve the Riemann-Hilbert problem by an algebraic ansatz. Okay, that's in fact how one can arrive at. That's how we can make the plots. You know, Deniz didn't show you a plot for m that's not a half integer or a quarter away from a half integer, and that's because he's using the algebraic method to find those solutions, right? So we're reducing it to a determinant, and we can evaluate this determinant on the computer. But otherwise, one has to solve the Riemann-Hilbert problem, unless someone out there can think of a way to solve that problem explicitly. So this maybe gets back also at Vincent's question from the last talk. You know, it is possible to think of this as some kind of iterated Darboux transformation of a certain background. And the background we're talking about here, the basic solution, is one that goes with like the minimal k, so k equals 0, but this remainder r is not either 0 or 1/4, but something else. And in those cases, the question is, can you solve that Riemann-Hilbert problem explicitly? And so far, we don't know how to do that.
Okay, thank you. And last question from Pavel. Can you unmute?
Okay, yeah, my question may be a little too general, maybe a little too naive, but Peter, because you have many different cases, it looks complicated, but still for general picture, can you just tell something general? So assume we have some domain where solution, you know, almost the same, but you have these separate cases actually when you're looking outside of this domain. So is that behavior, could be some cases when deviation really grow very strongly outside of this domain where you have the same solution?
Well, you know, yeah. You know, these different solutions have to satisfy different kinds of boundary conditions. So you certainly expect something, you know, detectable, right, far away. But what's interesting really is that the fact that you can't tell the difference if you, at least at the leading order, if you look inside of this hamburger region, which kind of, it's a little disappointing because you might think that you could predict, for example, a rogue wave by making some sea surface measurements, you know, just before, right, before the thing appears. But what we're seeing is actually, you can't tell the difference between a rogue wave, a soliton, you know, something else, if you look in a certain hamburger region of the space-time, right? So it's a little bit disappointing from that perspective. Maybe you'd have to detect it from, you could say for sure, like if you, how far away you'd have to be to tell the difference, you know?
Yeah, it looks very pessimistic, but kind of experience from, for example, optical fibers. It's well known that kind of perturb amplitude much more difficult than perturbing phase. Is that distinction, I mean, of complex solution, is that you have this distinction, and when you perturb in your domain solution, what will be outcome?
Yeah, I mean, so I'm not sure how to answer the question, except I can say that it's possible to solve the linearized problem, if that helps. You know, if you were going to perturb the solution from the point of view of this Riemann-Hilbert problem that we start with on the circle, you can, you know, you can do the usual kind of linearization, right, where you bring in the perturbation through some Fourier transforms and whatnot, and then you modify the Riemann-Hilbert problem and you compute the solution of the linearized problem. That's possible, and we did that for the Peregrine case in our paper with Deniz. But yeah, it could be interesting. I think it would be interesting to try.
Mm-hmm. Thank you.
Sure.
Thank you very much. Thanks again for excellent talks, Deniz and Peter. And I guess, well, we can continue during the discussion after Gino's talk. And we'll see you in kind of 20 minutes. Sorry for stealing a bit of